All right, welcome back to the deep dive. Today we're going to be getting into something that's pretty, fundamental to how your car works, but you probably don't think about it too much.
Yeah, it's kind of hidden away.
Exactly. We're talking about all the communication going on between the electronic parts inside your car. Think of it as the car's central nervous system, yeah, constantly sharing all this vital information.
It's a great analogy. And we've got some great source material today that dives deep into the technical details of these in-vehicle networks.
Right. We're going to be taking a close look at this presentation from the Automotive Security Research Group, and I think it gives us a really cool behind-the-scenes look at how these modern vehicles actually function.
Absolutely. It's fascinating stuff.
So basically what we're going to do today is, and this is really key, if you want to understand modern car tech, we want to figure out what the different types of in-vehicle networks are, why car makers use different systems instead of just one best solution, and then get a good handle on their strengths and weaknesses.
Yeah, I think that's a great way to frame it. We're going to give you a kind of shortcut to understanding this crucial part of how cars work.
Exactly. So let's just jump right in, shall we?
Yeah.
First things first, I guess. What is an in-vehicle network?
Okay, so in simple terms, an in-vehicle network is a specialized kind of networking technology designed just for cars.
Okay.
And its main job is to allow all these different electronic control units, these ECUs, to talk to each other.
Right, the ECUs.
Yep, and they need to share all kinds of data efficiently and, importantly, safely. So this could be sensor readings like your anti-lock brakes or checking wheel speed, engine temperature,
Okay, I see.
or it could be really complex calculations from the engine control unit, or maybe just status updates from different parts of the car.
So just to be clear, when we talk about these networks, we're talking about the physical wired connections inside the car, right?
Exactly. We're not talking about the wireless stuff like Bluetooth for your phone or the
Right.
car's Wi-Fi. We're talking about the hardwired pathways, the copper wires, maybe some fiber optic cables that make up the backbone of communication in a vehicle.
That makes sense. So it's like the nervous system, like the actual wires and stuff?
Yeah, exactly. And one thing to remember is that car makers don't just choose one type of network and use it for everything in the car.
Oh, interesting. So there's like a whole variety of them in there.
Yep. They carefully decide which network technology to use for each specific job. Controlling the engine might use a different network than, say, the entertainment system. It all depends on what that system needs to do.
So there isn't one like magic bullet network that does it all.
Right. There's no one-size-fits-all solution. Each network has its own strengths and weaknesses.
Okay, that makes sense. So then when we think about how all these different electronic parts are connected, I remember seeing something about network topologies in the research. What are those exactly?
So network topology just refers to the way all these different nodes, the ECUs, are connected within the network.
Okay, so like how they're all laid out?
Exactly. Think of it like a roadmap of the network. You've got a few common ways to arrange these connections. There's mesh, fully connected, sometimes called full mesh,
Okay.
star, ring, and the common bus.
Lots of options.
Yeah, and while you might see some of these other layouts in specific cases, the most common one for in-vehicle networks is the common bus topology.
Common bus.
Yeah, so imagine it like this. You have one main road, and all the ECUs are like buildings along that road. They can all send and receive information on that shared road at the same time.
So it's like everyone's sharing the same highway.
Exactly. And that's how the CAN bus, which we'll talk about in detail soon, operates.
CAN bus. Got it.
It's pretty simple to set up, and it's cost-effective, which are big pluses when you're making millions of cars.
Right, of course. But I think I remember reading something about a downside to this common bus setup. Something about a single point of failure. That sounds a little scary, honestly.
Yeah, that's a very valid concern. Because everything relies on that single communication pathway. If something goes wrong with the bus itself, it could mess up communication across multiple systems. That's why for super critical stuff, where reliability is absolutely essential, they sometimes use other topologies, but those are generally more expensive or complex to set up.
Like which ones? You mentioned fully connected and matched.
Exactly. A fully connected topology where each ECU has a direct line to every other ECU has a ton of redundancy. If one connection breaks, there are tons of other ways for them to communicate. But as you can imagine, that gets really expensive and adds a lot of weight, which is something car designers try to avoid. Mesh networks are kind of a compromise. They give you some redundancy without needing a crazy amount of wiring.
And what about those other ones, star and ring?
So star topologies where everything connects to a central hub are becoming more popular with the rise of Automotive Ethernet, which we'll get to later.
Okay.
If one connection fails, it doesn't necessarily bring down the whole network, but that central hub becomes super important.
Makes sense.
Ring topologies are less common overall, but they are used in the most network, which is mostly for multimedia stuff. And, this idea of matching the topology to the need is important. In most, that ring can actually help if there's a break in the connection because the signal can potentially keep going the other way around the ring.
Wow, that's clever. It really shows how important reliability is in a car.
Absolutely. I mean, we're talking about machines that move fast and carry people, so safety is paramount.
Yeah, no kidding. So the way you design the network has huge safety implications.
Huge, yeah. The choice of both the topology and the underlying network technology itself is all about making sure the vehicle operates safely and reliably. And that's why certain technologies have become the go-to for specific applications.
Okay, so let's talk about those technologies. From what I read, it seems like CAN bus is the big one, right? Like the most common one. Why is that?
You got it. CAN, which stands for Controller Area Network, is definitely the most widely used in-vehicle network tech today. It's become so common that it's essentially a standard. In fact, it's even mandated for onboard diagnostics in the US and Europe.
Really? Wow.
It was developed by Robert Bosch, and the most common versions you'll find are based on the C10 2.0b specification. And that spec uses 29-bit arbitration identifiers, which sounds complicated, but it's actually pretty clever.
Arbitration identifiers. Can you break that down a bit for me?
Sure. So imagine it as a way to manage all the communication traffic on that shared bus we talked about earlier.
Right, the highway analogy.
Exactly. Now, CAN uses a multi-master bus architecture, which means any ECU can try to send a message whenever it wants.
So it's a free-for-all.
Well, not exactly. They need a way to prevent crashes, right?
Yeah.
So that's where these arbitration IDs come in. Within each CAN message, there's this identifier that essentially tells you what kind of data is being sent, but not specifically who is sending it or who it's going to.
Oh, I see. So it's less like a specific address and more like a label for the type of information.
Right. And the really cool thing is this is also how the network prioritizes messages.
Prioritizes, like some messages are more important than others.
Exactly. So critical things like messages from the ABS system can basically cut in line and make sure they get through super fast. It's this prioritization scheme that made CAN so successful.
That's really smart. So it's not like your home network where each device has a specific address. It's more about how important the information is.
Exactly. The message itself determines its priority. And in the original CAN spec, each message could carry up to 8 bytes of data.
Gotcha. So in the research, they mentioned a few different flavors of CAN. There's high-speed single wire and low-speed fault tolerant. Let's start with high-speed since it seems like the most common. How does that work?
Okay, so high-speed CAN, sometimes called dual-wire CAN, is what you'll find in most critical systems that need more bandwidth.
Bandwidth.
Yeah, like being able to send more data per second. And it uses something called differential signaling over twisted pair cabling, which sounds complicated, but it's all about making sure the signal isn't disrupted by electrical noise.
Noise. Like interference.
Exactly. Cars are full of electrical noise from all sorts of things, like the engine, motors, even the spark plugs. All that can mess with the signals being sent over the wires.
Right. That makes sense.
So the twisted pair cabling is like this. You have 2 wires carrying a signal, and they're twisted together really tightly. This helps reduce interference because any noise will likely hit both wires equally.
Oh, so they're like canceling each other out.
Kinda, yeah. And then with differential signaling, the receiver is looking at the difference in voltage between the 2 wires. Even if there's some noise, that voltage difference will stay pretty consistent so the signal gets through. It's like listening to the difference between 2 sounds. If both sounds get louder at the same time, the difference between them is still clear.
Wow, that's a really good way to explain it.
Glad it helps. And in terms of speed, high-speed CAN can theoretically go up to 1 megabit per second, but in real-world car applications, you'll usually see it running at 125, 250, or 500 kilobits per second. And the length of the cable matters too. Longer cables mean you need to slow things down a bit for reliability.
So faster is not always better, it sounds like.
Right. There's always a trade-off. And one more thing I'll mention is termination resistors. These are little components at the ends of the bus that prevent the signal from bouncing back and causing problems. Think of them like shock absorbers for the signal.
I gotcha. So what about single wire CAN?
Single wire CAN, it's basically a more basic, stripped-down version.
Okay.
It's designed for things that don't need a ton of bandwidth or super high reliability.
Hmm.
And as the name suggests, it uses just one wire for communication.
But I'm guessing there's some downsides to that.
Yeah, there are trade-offs. It's a lot slower, maxing out at 33 kilobits per second. And because it doesn't use differential signaling, it's a lot more vulnerable to that electrical noise we were talking about. It's definitely a compromise.
Right. So I guess it wouldn't be used for anything critical.
Not really. It was used in some older cars for things like power windows, door locks, things like that, but it's becoming less common now.
Makes sense.
Yeah.
Okay, and last one was low-speed, fault-tolerant CAN 10. That sounds like they really focused on reliability with that one.
Yep, that's exactly the point. It's all about making sure the communication keeps going, even if something goes wrong.
I like that.
So one way it does this is by spreading out those termination resistors we talked about earlier. Instead of just having them at the ends of the bus, they're distributed across multiple nodes. So if one node fails, it doesn't bring down the whole bus.
Oh, I see. It's like having backups.
Yeah, exactly. It's more resistant to individual failures. And it also often uses higher voltage differences for signaling, which makes it less sensitive to noise. Some versions can even switch to a single wire mode if one of the wires breaks, which is pretty cool, but it's more expensive and usually limited to 125 kilobits per second, so it's not as widely used as high-speed CAN.
Right, so it's a trade-off again. Reliability versus speed and cost.
Exactly.
Okay, so zooming out a bit, where is CAN used in a modern car overall? It seems like it's in a lot of different places.
Oh yeah, CAN is all over the place. It's like the central nervous system of the car, really. You'll find it in the instrument cluster, the engine, transmission, HVAC, headlights, brake lights, power windows, even the GPS. It's basically the main communication backbone for a ton of different functions. So even if your infotainment system acts up, which might be on a completely different network, your brakes will probably keep working fine because they're on something robust like CAN.
Wow, that's amazing. It really is a critical part of how the car works.
It is.
Okay, let's move on to LIN, the little brother of CAN. What's its role in all of this?
So LIN stands for Local Interconnect Network. It came after CAN, and it was basically designed to be a cheaper solution for things that don't need high speed or super high reliability. CAN is already pretty inexpensive for in-vehicle networking, but LIN takes it even further by using simpler hardware.
Okay, so, what are the main differences between LIN and CAN?
Well, for starters, LN uses these things called UART transceivers, which are much simpler and cheaper than the ones CAN uses. And it's also a single wire network, like that single wire CAN we talked about, but it operates on a master-slave architecture.
Master-slave, what does that mean?
It means there's one master device that's in charge of all the communication on the bus, and it has up to 16 slave devices connected to it.
Okay.
The master controls everything, and it works based on a predefined schedule. So the master will send out a header, which is basically a request for data, and then the corresponding slave that has that data will respond. It all happens in a very controlled and predictable way.
So it's a bit more rigid than CAN, which sounds like it's more of a free-for-all.
Yeah, that's a good way to put it. In CAN, anyone can try to send a message at any time, and the arbitration system sorts it out. But in LI, the master decides when everyone gets to talk. And this actually has a benefit. It guarantees a very specific timing for communication, which is important for some applications. It also has some basic error detection built in to make sure the data is correct.
So LIN is slower and less flexible, but it's cheaper, and the timing is very predictable.
Exactly.
So where would you typically find LIN in a car?
LIN is typically used for things that don't need super fast communication or a lot of bandwidth. So things like power seats, adjusting lumbar support, electric mirrors, maybe power windows in some cases. Basically anything where a little delay wouldn't be a safety concern.
Got it. Okay, let's move on to FlexRay, which sounds like it's even faster and more complex than CAN. It was described as a sort of next-gen CAN.
Yeah, that's a good way to think about it. FlexRay was created to handle things that CAN just couldn't, especially when it comes to safety-critical systems that need really precise timing.
Yeah.
So it's designed to be super reliable. It uses 2 separate communication channels between each node, which means there are 4 wires per connection. This gives it redundancy. If one channel fails, the other one can take over. But of course, that makes it more expensive and complex to set up.
So it's like double the wiring for double the reliability.
Pretty much. And it can handle much larger data payloads than CAN, up to 254 bytes per frame. And it's especially good for things like X-by-wire systems.
X-by-wire.
Yeah, things like electronic throttle control, steer-by-wire, brake-by-wire. These systems replace traditional mechanical connections with electronic ones, and they need super precise and reliable communication. FlexRay's theoretical maximum data rate is about 10 megabits per second, which is way faster than classic CAN, but it's a proprietary protocol, which means it's more expensive and harder to work with.
So as cars became more sophisticated, they needed something like FlexRay to handle all the extra data and make sure those critical systems worked perfectly.
Exactly. It's all about keeping up with the increasing demands of modern vehicles.
And then there's CAN-FD, which stands for Flexible Data Rate CAN. It seems like it's trying to bridge the gap between traditional CAN and those higher speed options.
You got it. CAN FD is basically an upgrade to classic CAN. It was designed to be compatible with older systems while also offering higher data rates for newer applications.
So kind of the best of both worlds.
You could say that. The way it works is pretty cool. It basically starts communicating like regular CAN to figure out who gets to send a message, but then it speeds up the data transfer after that. It's like it shifts gears once the message priority is established.
Interesting. So it still can, but faster when it needs to be.
Right, but this can sometimes cause problems with older CAN controllers, which might see those faster messages as errors, so it's not perfectly backward compatible. But the big advantage is that it can transmit a lot more data in each frame. It can handle up to 64 bytes of data, which is 8 times more than classic CAN, and its theoretical maximum data rate is about 8 megabits per second, which is getting pretty close to FlexRay. In the real world, you'll probably see it running at around 6 to 7 megabits per second.
Wow, that's a huge improvement over classic CAN.
It is,
Yeah.
and it lets car makers get more performance without completely abandoning the CAN ecosystem.
Okay, let's move on to MOST. The name itself, Media-Oriented Systems Transport, suggests it's all about the entertainment side of things.
That's exactly right. Most is all about high-speed multimedia. Things like infotainment systems, fancy audio systems, video streaming to screens in the car, that sort of thing. And it usually uses a ring topology, which we talked about earlier. And this ring setup has a nice benefit. If one connection breaks, the data can potentially still travel the other way around the ring, so you don't lose everything.
That's a nice backup.
Yeah.
So MOST is all about making sure your movies and music keep playing smoothly.
Pretty much. And another cool thing about Most is that it was one of the first in-vehicle networks to use fiber optic cables.
Fiber optics, that's like super high tech.
It is. And fiber optics have a big advantage. They're immune to electromagnetic interference. So you get a really clean signal, which is perfect for audio and video.
Makes sense. And I guess since it's all about multimedia, MOST isn't used for critical safety systems, right?
Right. It's not about controlling the brakes or the engine. It's all about bandwidth, about moving lots of data quickly. And there are different versions of Most that offer different speeds. Like you have Most 25, 50, and 150, which refers to the speed in megabits per second. And they can use different types of physical media like fiber or even copper in some cases. And it's kind of interesting, Most was actually considered as a possible base for implementing Ethernet in cars at one point.
Oh, wow. That's a good segue into what's often called the cool kid of automotive networking, Automotive Ethernet.
Yeah, that's the new hotness for sure.
It seems like there's a lot of excitement around Ethernet.
Definitely. Automotive Ethernet is this new, high-powered, dynamic technology. And it is, at its core, similar to the Ethernet you use at home for your computers.
Okay.
But of course, it's been adapted for use in a car. So for instance, it often uses just 2 wires for data instead of 4, but it's still relatively new to the car world, so it's not everywhere yet.
Right. But I'm guessing its biggest draw is that potential for crazy high bandwidth, right?
Absolutely. Ethernet is all about speed. Unlike the other networks we talked about, it's inherently point-to-point communication. This can make it a little trickier to scale up to a large number of devices. You often need extra hardware like switches. But the potential for bandwidth is huge. I mean, we're talking data rates up to 10 gigabits per second. That just blows the other technologies out of the water.
10 gigabits, that's insane.
It is. And this isn't just about faster infotainment systems. It's about fundamentally changing how cars are designed. With that kind of bandwidth, you can start thinking about more centralized processing, maybe even over-the-air updates for the core functions of the car. Things that were just impossible before are now becoming possible with Automotive Ethernet.
So it's not just about entertainment. It's about the whole future of how cars work.
Exactly. It has the potential to revolutionize the industry.
But I think the research cautioned against using Ethernet for everything in the car.
Yeah.
Why not just go all in on the fastest option?
Yeah. Well, there are a few reasons. Cost is a big one. Setting up Automotive Ethernet, especially at those super high speeds, is still pretty expensive compared to something like CAN. or LIN.
Hmm.
And because it's newer, it doesn't have the same long track record of reliability in every possible car situation. And remember, the automotive industry is very cautious about safety. They don't like to adopt new tech until it's been proven for years and years.
Makes sense.
Also, because Ethernet is point to point and might need those switches we talked about, that can create new points of failure. And the ECUs themselves need more processing power to handle Ethernet, which also adds to the cost and complexity. So it's not just about having the fastest connection, it's about finding the right balance between speed, cost, reliability, and what that specific system in the car needs to do. It's like that old saying, you don't need a fire hose to water a small plant.
Right. You need the right tool for the job.
Exactly.
Well, this has been a really amazing look into the world of in-vehicle networks. So much going on under the hood that we never even think about. What would you say is the most important takeaway for our listeners?
I think the key thing to remember is that there's no one best in-vehicle network. It's all about choosing the right technology for the specific job. Car designers have this whole toolbox of different networks, each with its own strengths and weaknesses, and they carefully pick and choose which one to use based on what they need to accomplish.
So even though we have these new high-speed networks like Ethernet coming in, it doesn't mean that older stuff like CAN bus is going away anytime soon, right?
Exactly. CAN is super reliable and cost-effective, and it's going to be around for a long time.
That's good to know. So as we wrap things up, what's one question or thought you'd like to leave our listeners with?
Well, I think it's important to consider how all this is going to evolve as cars get even more complex. We're talking about self-driving cars, electric cars, cars that are constantly connected to the internet. All this is going to create huge challenges for in-vehicle networks. How do you handle even more data? How do you keep all those systems secure from hackers? How do you make sure the communication is fast enough for real-time control? And how do you manage the cost and complexity of all this?
Right. It's a lot to think about.
It is. So I think the big question is, what kinds of innovations are we going to see in in-vehicle networks as the automotive industry tackles all these challenges?
It's fascinating to think about how this is all going to play out. Thanks so much for joining us today and sharing your expertise. It's been a really insightful conversation.
You're welcome. Glad to be here.
And for our listeners, thanks for tuning in to The Deep Dive. We'll see you next time.